Hello everyone, thanks for joining the DeepStream Technical Deep Dive. My name is Paul Shin, and I'm leading the Object Tracker development in DeepStream team. In this session, we're going to talk about multi-object trackers in DeepStream today. First, just a little bit of background about DeepStream. DeepStream SDK helps users to build AI-based streaming analytics pipelines. So, given a set of video sources, users can compose a pipeline with modules for capture and decode, pre-processing and batching, AI inference, and multi-object tracking and analytics with visualization. Among all these, we are going to deep dive into the Object Tracker module today. The first question is, why need object tracking? The most fundamental functionality of multi-object trackers is to solve the ID assignment problem. Given a video, there could be many objects in a frame, as you can find in the left side figure. For the same object, we want to assign and keep the same ID over multiple frames. That is the unique problem that object trackers are supposed to solve. Also, when we track objects, we wish it to have the same ID for the same objects for a longer period of time, ideally for the entire duration of the object's presence in the scene. To assign the same IDs persistently over time, the object trackers should be robust against occlusions and visually similar objects nearby. If you look at the top right figure, a vehicle undergoes a full occlusion by another vehicle. The object tracker is expected to keep track of the vehicle despite all those occlusions. If you look at the bottom right figure, there are two ladies who have purple jackets and black pants. The object tracker is again expected to keep track of them separately, although they are visually similar and they are adjacent to each other. Then why would we want to use object tracking even if ID assignment is not really needed? It is because it enables temporal analysis on each object. If we can do persistent ID assignment over time, it allows to generate the history data of each object. For location data, it is called as trajectory. Once we have this per object history data, we can improve the accuracy, especially when a state estimator is used in object tracker, for example, Kalman filter, word particle filter, etc. The object detection by a neural net model may have some noise in bounding box location and sizes, so there are measurement noises. State estimators help us to reduce such noises and estimate the true location or true bounding box. Another benefit is about the detection errors. The detectors like YOLO or PeopleNet may generate false positives and false negatives. These can be mitigated by temporal analysis, and this is something we will look into more closely today. The third benefit is related to the performance. In case an object tracker is equipped with a visual tracking capability, just like in NvDCF, it allows least frequent inference. In other words, skipping frames for inference, while the object is still tracked every frame. This improves the performance at the minimal cost of accuracy. So essentially, this can improve the trade-off between accuracy and performance. So we have talked about why we need and why we want to use object tracking. Then now we want to talk about what DeepStream has in terms of object trackers. Actually, DeepStream offers three types of object trackers: IOU, DeepSORT, and NvDCF. Just wanted to note that before DeepStream 6.0, we had separate low-level tracker libraries for each tracker type. But now we have only single low-level tracker library called NV Multi-Object Tracker lib that implements all multi-object trackers offered in DeepStream using the unified tracker architecture. Each tracker type can can be configured through just simple configuration changes. IOU tracker is typically a bare minimum tracker that has only the data association module for ID assignment. But our implementation of IOU tracker includes the error handling mechanism, which is inherent in the target management module of our unified tracker architecture. Thus, it can handle false positives and false negatives from the detector. More details about this error handling will follow soon. IOU tracker also has a trajectory management module simply because that module is responsible for generating unique IDs. All other types of trackers are implemented on top of the IOU tracker. DeepSORT is our own implementation of the well-known DeepSORT tracker, which uses a neural net model to extract the VID feature for data association. It's currently in alpha release mode, and most of the features are implemented, and the accuracy is almost comparable to the open source implementation. Compared to IOU tracker, it has a Kalman filter as the state estimator, and it uses VID-based matching score as a data association metric, as well as proximity between objects. NvDCF is our flagship multi-object tracker that has the best accuracy and performance. It uses the discriminative correlation filter for visual tracking and uses the relative correlation response as the visual similarity score. We will talk more details about NvDCF in the later slides. Just to be on the same context, we are going to briefly review how multi-object tracking typically works in conjunction with object detection. Given a video frame, object detector detects a set of objects and provides a set of bounding boxes with confidence values to the downstream modules like the object tracker. In this sample video frame, there are 4 detected objects, indicated by red bounding boxes. Because the frame number is 0, this is the very first detection, and all of these are newly detected objects. The target management module instantiates a target tracker for each of these newly detected objects. Because we now have target trackers for the newly detected object, we can predict the location of these targets in the next frame, which are represented as the green bounding boxes. These predicted bounding boxes can be generated using the state estimators like a Kalman filter, or they could be just the same bounding box in the previous frame if there's no prediction capability in the object tracker. In this frame, we also have a set of bounding boxes from the object detector in PGIE, which are represented as red bounding boxes. Given the detection and tracking bounding boxes, we now perform data association. Typically, a score matrix is generated between the two sets, and the matching is performed based on the score matrix in such a way that the total matching score over all the matches is maximized. When the matching process is completed, there will be 3 sets of bounding boxes. The first set is the matched detector tracker bounding box pairs, which consists of the bounding box pairs found by the matching algorithm. This means that an existing target has a new measurement from the detector, so we can perform target state updates with a new measurement. Some existing targets may not be detected in a new frame. Then these would be put into unmatched tracker bounding boxes. Because this target is not detected, it is likely that the target is no longer present in the scene. Then the target management module may decide to terminate the target. Some detector bounding boxes may not have corresponding targets. Then these would be put into unmatched detector bounding boxes. Because there are no corresponding targets, these are considered as the new objects. The target management module would instantiate target trackers for them. However, what if an existing target is not matched because of false negative by the detector? Although the target still exists in the frame, the detector may miss it. Also, what if a new object is detected because of false positive by the detector, meaning that actually there's no object in the bounding box? Neural nets are not perfect, so this may happen. So these are the types of measurement errors that the tracker has to deal with to perform robust tracking. To handle the errors from the detector, we employ several approaches. To handle the false positives from the detector, the first approach we use is called late activation. Whenever a newly detected object is provided, a new target tracker is immediately instantiated, but in tentative mode, and activated only if it survives for a number of frames, which is configured by probation age. Essentially, every new detection undergoes a validation period to see if it is consistently detected over time. If the target is not detected consistently during this tentative mode, this target is terminated early, so we can filter that out. This approach is called early termination. We say early because if the targets survive this period and are validated, they are allowed to be tracked in background for a much longer time, which is what we are going to talk about next. Some of the targets may not be matched due to false negatives from the detector. Then we use an approach called shadow tracking. So we allow the tracker to keep track of the object in background for the number of frames that is specified by max shadow tracking age. During this period, the tracker does not report its output to the downstream, because it could also be the case that the object is actually not present in the scene. But these tracking data are stored internally as past frame data. Because the target is not associated with any detector bounding box, this target is put into inactive mode, and an internal variable called shadow tracking age is incremented. If the target is associated with a detector bounding box later, then it will be put back into active mode and start reporting the outputs. And if there's any past frame data stored, then it will be passed to the downstream as a part of user meta. NvDCF tracker is built on top of the IOU tracker by enabling visual tracking module and the Kalman filter-based state estimator module. And we are going to look deeper into the visual tracking module of the NvDCF tracker, which is based on discriminative correlation filter. Given a bounding box of an object, it defines a search region around it. NvDCF then learns a correlation filter that would yield the max response value at the center of the object. If we apply the learned correlation filter to the next frame, we would get the max response value at the new location of the same object, which is represented as the dark red spot in this figure. This visual tracking capability of NvDCF allows the target to be tracked even during non-inference frames. Basically, NvDCF allows skip frames in inference while still being able to keep track of the targets. This greatly improves the performance of the perception pipeline at a very low cost of accuracy. In this example, let's say the inference interval at PGIE is 1. Meaning that the inference is carried out every other frame. At frame 0, this frame is inferenced, so we have the detector bounding boxes. And the visual tracker module creates the correlation filters for each object. At frame 1, there's no inference performed, so no detection bounding box is available. However, the visual tracker module applies the learned correlation filter to localize the object in the new frame around the predicted target location. At frame 2, the PGIe module performs inference and generates the detector bounding boxes. At the same time, the visual tracker also performs the localization. For the matched pairs in the data association module, there are two measurements generated for the same target, one from the detector and one from the tracker. Both of them are actually fused together in the Kalman filter based on their measurement noise variance. There are some parameters that affect the performance and accuracy, and these parameters determines the trade-off between accuracy and perf. In terms of visual feature types, we have color names that represent the entire color space in 11 channels. We also use hog features that encode the edge features in 18 channels. So depending on the use cases, users can decide which one to enable, but color names and hog features are pretty complementary, so I would recommend using both of them for most cases. Feature image size level parameter determines the resolution of the internal representation of an object in each tracker. It ranges from 1 to 5, and a higher level would increase the accuracy, yet at the cost of memory and perf. The detection interval in PGIe also heavily affects the perf, so this is something to be tuned when optimizing for performance. Now, we are going to look into a case study where we use TRAFFICCAMNET for applications like traffic monitoring. In this sample video, we can see that there are many occluding objects present in the scene. There is a large traffic light pole at the center of the video, and there are many vegetations along the road that causes full occlusions for a pretty long time. Also, the vantage point from the camera is pretty shallow, so there is a large degree of self-occlusions happening among vehicles. All of these contributed to inconsistencies in object detections in the video. This happens not only to the TRAFFICCAMNET, but also to all the other neural nets, because there's no perfect detector, and every detector has its own precision and recall characteristics. And also, this particular sample video is actually quite challenging for the reasons that I mentioned earlier. Because of the self-occlusions and partial full occlusions, some typical issues you may find from the video in the last slide would include like false negatives, as you can see in this figure. There are two cars behind the traffic lights, but they were not detected. Double detections is like a single bounding box captures multiple cars in it. Off detection is that bounding box is not quite right in terms of location and size. It is not centered at the object center. There could be false positives as well, just like in this figure. There is only one car in this figure behind the traffic light, but it is detected as multiple cars. Partial detection is not actually an issue from the object detector's point of view, because it is what it's supposed to be. It captures only the visible part of the object. But still, this poses challenges to the tracker. There could be some nasty cases as well, where multiple detection errors are combined, like in this figure. The white truck has 3 bounding boxes with different types of errors. All of these errors are the challenges to the tracker, because the tracker is expected to keep track of the objects even with all these detection errors. For the given sample video, we just want to try using NvDCF tracker with the performance-oriented config parameters to see how it works. The color-coded lines and dots represent the whole trajectory of each object. This 106 in here represent the target ID, and 78 represent the tracking age, meaning how many frames this target has been tracked. Each trajectory data shows the lifespan of an object. So we can see how long an object is tracked and when it is terminated. If you look at this area where the vehicles undergo partial or full occlusions by the trees, we can see that many trajectories just end there, implying that the tracker were not able to keep track of the objects through the trees. Let's see the video to see if our observations are correct. This video is created using some simple visualization tool and the kitty dump outputs from DeepStream. As expected, when a vehicle goes behind the trees, it is most likely lost, and new target ID is created when it appeared again. Also, many vehicle tracks are lost when they go behind the traffic light pole. So when there's pretty heavy occlusions, the perf-oriented setting for NvDCF tracker doesn't do a good job. To get better accuracy, I just want to start with the highest accuracy setting, meaning the most power-consuming setting. So we know what is the attainable accuracy that we can achieve. And then we can try trading off some accuracy to meet the performance budget if there is. Please note that in this case study, we analyze the results only qualitatively, but it is always best to use a dataset established specifically for your own use case, and then perform accuracy analysis on the result using the accuracy KPI of your choice that matters most to your application. I picked the accuracy-oriented config file for NvDCF and then changed the feature size level to 5, which was 3 by default. In fact, the NvDCF accuracy config was tuned more toward pedestrian tracking. So this may not work the best for vehicle tracking, and certainly there are a lot of room for tuning for vehicle tracking use cases. In this snapshot, now we can see that more trajectories pass through the trees and also the traffic light pole, meaning that the tracker seems to be more robust to those occlusions. Let's check the video and see if that is the case. In the video, we can see some improvements. As mentioned earlier, the tracker works better even in the case of occlusions like behind the traffic light pole and the trees. But still, it's not quite there yet because we see many failures. To tune for a particular use case like intelligent traffic system, we first need to have some insights and understanding about the object's behavior. One thing that we can observe is that vehicles tend to have more linear and monotonous motion compared to pedestrians. Given these insights, we want to tune the motion dynamics parameters like the variance for the process noise and the measurement noise. Basically, the idea is that we want to give more confidence on the past trend of the motion than the immediate measurements. To do that, we want to lower the process noise variance while increasing the measurement noise variance. The process noise variance for location was 2.0 by default. So let's try 0.2, which is 10 times smaller. The process noise variance for size was 1.0 by default. So let's try 0.2 as well, which is now 5 times smaller. The default measurement noise variance for detector was 5 times smaller than that for tracker. but we saw that the detector doesn't seem to be very reliable for this particular video. So let's make them the same. By no means I'm saying this is the optimal parameters, but rather I'm demonstrating how we can go about tuning and see if we are going in the right direction. If the result of this make things any better, then we would know that we are going in the right direction, and we can further tune the parameters along the same line. Let's check the updated result with these tuned parameters. Now we can see even more trajectories pass through the trees and traffic light pole. So looks like it's working well. Let's check the video. We can see that there are list ID switches and the trajectories are passing through the occlusions. If you look at the black SUV with ID 1, it has been tracked although there were full occlusions by other vehicle. There was a truck, yes, this one, that obstructed this ID number 1, but it was tracked. There are still some issues, and we can further analyze those failure cases and perform more tuning on the tracker side. There are some false positives in these areas, and to suppress those false positives, you may want to increase probation age to filter them out. But if the false positives are persistent, we cannot filter them out in the tracker, and also increasing probation age may increase the false negatives. Instead, you may configure the PGI configs in such a way that the precision increases at the cost of recall, and tune the tracker so that it can compensate for the false negatives. To do that, we may try lowering probation age while increasing max shadow tracking age. Anyways, the updated parameters made things better, and we can verify it qualitatively. Again, it will be better to use a dataset-based quantitative evaluation for tuning. Otherwise, we may end up doing case-by-case tuning, and it may help for one case, but it may negatively impact on other cases.